So it's coming across here, it's going into this detector here, and then out of the speaker, which means that if I stand in the way of it, then it goes off. So the information is really being transmitted on there, you can see. If I do that, then so the communication works, and we could do that, but the problem is exactly what I showed there. If it rains, then it stops. So you can't communicate if it rains, and in general, that's not a particularly brilliant way to communicate. What we need to be able to do is take the laser to where we want it without anything getting in the way. So we can show you how that works using our display lasers and this tank of water over here. So if we shine the laser up into the tank of water, we okay? Can we get the laser up into the tank of water? Once everyone gets out of the way of the laser, we can shine that. There we go. So what we've got here is a tank of water, and the beam from the laser is coming up here. It's coming up, hitting the tank here, and coming up to the surface here. And the interesting thing about this, and the key point, the thing that really makes the whole thing work, is that when it hits the surface of the water, even though that's a transparent interface, you can see that apart from some scatter, pretty much nothing comes out. So that transparent interface between the water and the air is 100% reflecting. And that's what makes the whole communications business work. So what's going on here, a sketch of this, the laser beam comes up, it hits the interface. If we hit it at these angles here, then a lot of it comes out of the water. As we tip the beam over, we get to a sharper angle, and we get to an angle here where that light is reflected completely back down into the water. And it's 100% reflection. There's a little bit of scatter here. And if it wasn't 100%, it wouldn't work, because we're going to bounce this light down something which is maybe 50 kilometers long. And if we lost any light at those reflections, then it would be completely gone by the time we got to the end. So this tank of water kind of shows you how we can put light down what we refer to as a waveguide, like an optical fiber, in order to get it to the other end. We can show you it in a bit more detail if we look at this jar of water here. So what we're going to do now is take this laser, focus it into this jar of water, and show you what happens. Hopefully get the bucket in the right place. So the laser's coming into the jar of water, and again, it's being reflected at the interfaces of this stream of water. And you can see that it really only, it starts to come out of the water jet only right down here. And, get that way. You can sort of see on this screen, you can see the bright spots where it's bouncing along inside the water and hitting the surface of the water. And even though the surface of the water is completely transparent, it's being reflected down inside. And that experiment was first done in the mid-1800s, but it looks much prettier with a powerful laser than it does with sunlight. So that's the principle by which we get data from one place to another. Obviously, streams of water, although they would be very entertaining to use as data sources, probably not that practical. And so what we can do is take the light, put it into the equivalent only made of glass, optical fibers. We've got one of these strung around the podium. There we go. Can we have the lights down a little bit so we can see this? So what you can see at the front there is a fiber that the laser's coupled into. With the fiber actually has a very tiny glass core. It's maybe 10 microns across. The whole fiber is only about 125 microns, which is about the diameter of a hair. And the bit that the light goes down is actually even smaller than that. It's about 10 microns. And we can tell that this process is doing what we think, because if David bends the fiber there, can you see that? When we bend the fiber, it no longer hits the interface at the right angle, and it comes out. So the light comes spilling out if we bend the fiber. And different colours actually come spilling out at different places. If this was a perfect optical fiber, you wouldn't see anything at all, but we don't use perfect optical fibers for this because it would make a very dull demonstration. But there's the fiber, as the light's going right, you can see the spool of fiber just about here. And the light's going onto that, and it will go a huge distance. Okay, can we get the lights back up? So, this is what it actually looks like. We maybe have those ones there down. That's great. This is what it actually looks like. It's this 10 micron size glass core. It's 125 micron size glass cladding. And then we put plastic over the top. It's incredibly strong, this stuff, but unless you scratch it and then it falls to pieces. How much light can we get? How far can we get the light down here? The loss, the units we quote it in is 0.2 dB per kilometre. That means a factor of 2 reduction in the intensity of the light over 15 kilometres of optical fibre. So factor of 2 is about what most sunglasses will do. So you can imagine that looking at the light from 15 kilometres away is the equivalent of sort of putting on a pair of sunglasses. It's the most transparent stuff that's ever been made. We can actually go hundreds of kilometres between repeaters, and that's why you can send optical fibre cables right across the ocean and things like that. That's this amazing transparency of the material. If we want to go farther, then we can go with one piece of fibre. We can actually do something, we can combine the two. We can take our laser and remove the mirrors, and we know what that makes. That makes an amplifier if we've got no mirrors. And then what people have worked out how to do is to actually put the laser inside the core of the optical fibre. And that means that now we can actually make an all-optical communication system. A piece of fibre, the light goes through, the intensity is dimmed until it gets to an amplifier, and then the intensity is boosted again, and then the light gets dim again. And we can, so that's how we do links across the Atlantic and links across the Pacific and things like that. We can transmit the light here over millions of kilometres. So how much data can we get down? One piece of fibre. The answer is astonishing. This is a record from last year. 250 million bits of information down one piece of fibre per second. So 250 terabits per second down a single piece of fibre. How do you do it? Well, we use the properties of the laser. We know that we can make the lasers in single colours. And so what we'll do is take maybe 128 or 256 different colours and put them down one piece of fibre. We combine them with something like the diffraction grating that we've got, and then we put them all down inside the fibre, and to first order at least, they don't affect each other when they're coming through the fibre. So when they get to the other end of the fibre, you just have another diffraction grating, spread them out. Each one of those can take data. So we use what we call wavelength division multiplexing, which uses the fact that the laser is this single colour. We also use different polarizations. So what can we do with 250 million bits per second? How many TV channels do you think that could carry? Any thoughts? It's actually 1.5 million HD channels down a single piece of fibre.
Jeez,
that's marvellous. That means you can have channel 4 plus 10 seconds, channel 4 plus 20 seconds. So that's some kind of idea of how I do this. But 1.5 million channels down one piece of fibre. How long would it take to download a movie? This is, it would be 66 microseconds. So it's 15,000 movies per second downloaded, which is a very good way to rack up a very, very large bill. Even more than that, if we look at, say, iTunes, most of you are probably familiar with the iTunes music store. It's about 43 million songs. You could download the whole lot in 11.6 seconds down one piece of fibre. And the one that I really like, the entire contents of Google. Now, it's quite hard to work out how much information Google stores, but essentially, if you snoop around and look at their server farms and all this kind of stuff, you can work it out. And this is essentially the whole internet, right? That's what Google stores. That's how it does its trick. 11 hours to move the whole internet from one place to another down a single piece of fibre, which is remarkable. It's about 10 to 19 bits. So you could download the entire internet overnight. So the capacity of one piece of fibre is absolutely astonishing. So at that point, you would immediately say, well, why can't I do that? Why is it that I can't do that all the time? And the problem is that when the data comes out, essentially, it's like trying to drink from a fire hose. You just can't deal with all that information. The electronics at the other end of the fibre just can't deal with it because the electronics isn't fast enough. So, oh yeah, sorry, there's one more point. How many phone calls at once down one piece of fibre? Phone calls were originally what we did on optical fibres, and the answer is more phone calls than there are people on Earth down one piece of fibre. Which is great, unless you happen to sell fibre for a living, in which case it's rubbish because you only sell one piece. The first transatlantic cable was in fact only 2 bits of fibre going one way, 2 bits of fibre going the other way. In that case, one of them was a spare. So there really was only one piece of fibre when they put the first cable out, because you didn't need any more. Because one fibre will do the whole trick. So, is it finished? No, it's not. That's the exciting bit from my point of view, because there's lots more research to do. Even though we can do these amazing things, people speculate that we'll be at the limit of what you can do in not very long. Less than 10 years, we'll have saturated what we can do with the internet right now, even given what these statistics I've just been giving you. So, we need to understand how to make it faster, because if you give people bandwidth, they'll just use it up. And as soon as people start downloading videos, and then HD videos, and then UHD videos, and you can use that bandwidth up despite how good it is. We need faster. The other thing we need is greener, because the amount of energy used up by all the switches and the hard disks and the computers on the end of the cables is getting to be very, very large. It's something like 10% of any heavily industrialized country. 10% of the energy usage is just in handling information. So that becomes very, very important, how to do this better. So there's an awful lot still to do, even though the fibers are fantastic. There's an awful lot to do with all the information on one end of the fibers, and the other, all the routers, the switches, and things like that. So it's still an area that has to be developed, but the developing that's been done so far is pretty amazing. So that's about the end of the show. If you've got good photographs, then please, or comments or anything like that, please tweet them or put them on our Facebook page. That'd be really great if you could do that.